Hi there. This is a re-recording of the talk, Everything You Want to Know About Optimization and Some You Didn't, that was originally given in May of 2018 at a Boston machine learning meetup. My name is Madison May. I'm a machine learning architect at Indico Data Solutions, where we solve big problems with small data. As a general outline of the talk, we're first going to be discussing some of the background necessary to understand what the rest of the talk will be about. We're then going to be discussing the ways in which some engineering implementation details can impact the learning dynamics of machine learning models. And then we're going to discuss some of the problems that recent papers have found with the optimization algorithm Adam and ways in which we might resolve those problems. Let's start by talking about ancient history. And by ancient history, I mean an optimization primer intended to get everyone on the same page for the rest of the presentation. First, some definitions. Loss is a differentiable measure of model error. The gradient is the direction of steepest descent at any point on the error surface. The loss surface, or error surface, is a visualization of how loss varies with parameter value. And the learning rate is how far to update parameters in the direction of the gradient after each gradient calculation. The most basic way of learning a model's parameter, given some training examples, is called gradient descent. And in this context, we're going to be talking about full batch gradient descent, where you compute the loss on the entire data set at once. The loss on the right-hand side of this equation is represented by J. Once we compute the loss, we're then going to compute the gradient of the parameters with respect to the loss, multiply that by some learning rate, and use that update to update the model's parameters, which are given by theta in the right-hand equation. It's not very common to use vanilla gradient descent in a full batch manner. Typically, when gradient descent is used in practice for optimizing neural networks, we talk about mini-batch gradient descent, where we're computing the loss on a small number of examples, rather than the entire dataset at once. We then use the loss computed by these parameters to compute a gradient and to update the parameters in the direction of this gradient estimate. At first glance, mini-batch gradient descent might appear to be inferior to full-batch gradient descent. You might say, well, if we're going to perform 1,000 updates on our model's parameters, we might as well have good gradient estimates, right? And in fact, you'd be right. If we were going to perform a fixed number of updates to our model, it would likely be good to have better estimates of the gradient of the model's parameters with respect to the loss at each given point in time. However, in practice, we don't fix the number of updates of our model. In fact, a much more practical value to monitor is the number of times we have to compute the gradient with respect to each example. In this setting, mini-batch gradient descent functions a lot like full-batch gradient descent, with the exception that we're updating our model's parameters within a given full batch. So after each mini-batch, we're changing the model's parameters. And this is equivalent to us using less stale estimates of good model parameters. The community has developed a bag of tricks to help stochastic gradient descent perform better in practice. One such trick is called momentum. And one such problem is the problem of stochastic gradient descent oscillating back and forth between two sides of a minima, which you can see illustrated here on the right-hand side of the slide. By keeping an exponential moving average of past gradients and using this component as part of our update term, we can help to dampen this variety of oscillation. In practice, momentum works much like the physical phenomenon, momentum. Momentum also helps model parameters to accelerate through flat areas of the loss surface. After we are given an initial gradient, we may not see an update for that same parameter for many batches if our gradients are sparse. In this setting, after giving the model an initial push via that first gradient, we want to allow the model's parameters to continue to coast for the next batches by using this momentum term and get through this flat region of the loss surface. SGD with Nesterov Momentum, also known as NAG or NAG, is an optimization on top of SGD with momentum that we found to provide better performance in practice. What NAG does is instead of measuring loss at the current parameters, we apply the momentum term of the previous update before measuring loss. You can see this illustrated here on the right-hand side. The small blue vector represents the new gradient term, and the large blue vector represents the portion of the update which is provided by the momentum term. In brown and red, we see how Nesterov accelerated gradient works. The brown component is the momentum term of the update, and the red component is the new gradient computed at the new estimate of the correct model parameters. The slight reformulation of stochastic gradient descent with momentum leads to better optimization behavior in practice, as you can see here on the bottom right, where we have a little visual of how some optimizers perform on a synthetic loss surface. It allows the optimizer to more quickly correct to changes in the loss landscape. In a similar way that using smaller batch sizes allows the model to adapt more quickly to changes in model landscape. Another problem we found with stochastic gradient descent is that it's often difficult to select a global learning rate hyperparameter that's appropriate for all the parameters of your model. We don't want the updates of individual parameters to vary too much. Different parameters require differently scaled updates. Adagrad, Adadelta, and RMSProp all use values of previous gradients, in particular the square of the value of previous gradients, to scale the current gradient estimate in a heuristic manner, and produce optimization methods that are significantly less sensitive to hyperparameters thanks to per-parameter scaling. Next, let's take a look at Adam. Adam is probably the most common go-to optimizer in current deep learning research. Like Adadelta and RMSProp-like methods, which we call adaptive learning methods, it stores an exponential moving average of squared gradients and uses that term to normalize updates. In addition, it has a momentum-like term where you store an exponential moving average of gradients. So it qualitatively behaves like a heavy ball with friction and tends to find flat minima of the loss function. Empirically, it leads to much quicker convergence than SGD in most cases and a reduced sensitivity to hyperparameters. However, as we'll discuss later, it turns out that although it converges quicker, it may not converge to optima that generalize as well as stochastic gradient descent. Here on the right, you can see Adam's update rule broken down into a couple component terms. You see there a momentum term and an adaptive learning rate term. So to quickly recap, we first have stochastic gradient descent, which is simply updating your model parameters by scaling the gradient. We then have momentum, which incorporates an exponential moving average of the gradient to allow for SGD to escape saddle points and to prevent oscillation over local minima. We have Adadelta and RMSProp, which use inverse scaling by exponential moving average of the squares of the gradient to help with sensitivity to hyperparameters. And we have Adam, which incorporates elements of momentum and adaptive learning rate methods. Next, let's dig into learning rate dynamics in a bit more detail and investigate how some things that you might typically think of as engineering concerns, like asynchronous training or the batch size used, can actually affect how the model learns. First, let's take a look at how batch size and learning rate relate to each other. In the paper, Don't Decay the Learning Rate, Increase the Batch Size, researchers found that batch size was roughly inversely proportional to learning rate in terms of how it affected model learning dynamics. So instead of using learning rate annealing, those researchers increased batch sizes for faster training times with roughly equivalent accuracies, thanks to increased parallelism. This is because we commonly monitor mean gradient over the batch rather than the sum of gradients over the batch in order to form a model update. In this formulation, the contribution of a given example to the gradient decays as batch size increases, in the same way that the learning rate decays the contribution of an individual gradient to the update. However, to make matters a bit confusing, the paper Finding Flatter Minima with Stochastic Gradient Descent found that both large learning rates and small batch sizes contributed towards stochastic gradient descent, finding flatter minima that generalized better. You can see the results of their experiments here on the right. The blue line, where the learning rate is 0.001 and the batch size is 50, is roughly equivalent to the red line, where learning rate is 0.005 and batch size is 250. When they multiply the learning rate by a factor of 5, they need to correspondingly multiply the batch size by a factor of 250. They similarly found that a large learning rate to batch size ratio leads to better generalization behavior than a small learning rate to batch size ratio. To a certain extent, this is exactly the same problem we talked about when we talked about mini-batch stochastic gradient descent versus full batch gradient descent. By using smaller batch sizes, we're providing more frequent weight updates for our model, and we have better intermediate parameter estimates that we compute gradients based off of. In addition, we have this high learning rate, which is acting like a regularizer, and it's helping the model to prefer flatter minima by jiggling model parameters out of local minima that are sharp. Just like there's a relationship between learning rate and batch size, there's a relationship between asynchronous training setups and momentum. Data parallelism is popular in the training of large machine learning models. You may have heard of it called hog-wild. And data parallelism acts similarly to the way momentum acts. Whereas momentum computes the running average of gradients, data parallelism computes the average of gradients over a batch of workers. If you found a momentum that works well in a synchronous setting, you should reduce your momentum parameter if you add in asynchronous training. This is to compensate for the increase in effective momentum provided by asynchronous training. Finally, let's look at the relationship between L2 regularization and your learning rate. The use of L2 regularization penalizes the magnitude of the weights of your model, and in doing so, decreases the average norm of the weights. When you decrease the norm of your weights, you need to correspondingly decrease your learning rate for optimal learning. Next, let's talk about learning rate scheduling. And in particular, let's first focus on learning rate annealing. For non-adaptive methods, the learning rate that is optimal at the beginning of learning is not the same as the learning rate that is optimal near the end of learning. Adjustments become finer later on in optimization, and the learning rate should be lowered to accommodate this. Here on the right, you can see an example of learning rate annealing, where we decay the learning rate after a given number of batch updates. We can think about learning rate annealing as being analogous to the way a painter might paint a canvas. Very early on, the painter might use a very broad brush to fill in the background in broad strokes. But later on, the painter needs a smaller, finer brush to fill in the details. In this example, the brush is somewhat analogous to a learning rate parameter. In the early stages of optimization, we need to make big updates to the model parameters because they were randomly initialized, likely. Later on in optimization, we need to carefully tune the model parameters to get best performance. We're making much smaller, finer adjustments to model parameters. It's not only necessary to strictly decay your learning rate. In fact, recent papers have seen quite good success with cyclic learning rates in a technique called Snapshot ensembling. Cyclic learning rates increase and decrease the learning rate on a schedule. Good optima are found when the learning rate is low, and high learning rates kick the model out of these local optima so they can settle into new, different local optima. If we save the state of the model parameters at each of these local optima, we'll find that the local optima are connected by a region of low loss on the loss surface. Averaging the parameters of these models at the local optima points acts quite a lot like ensembling distinct models does. And we find that the model produced by averaging the parameters of all the individual models generalizes quite well because there is a large flat area of the loss surface in the middle. This might actually be the largest practical takeaway of this talk, so I would highly encourage you to read papers like Snapshot Ensembles, Train 1, Get N for free, if you're interested in seeing good changes in empirical results that you can get from making changes to your optimization strategies. Finally, let's get to the heart of our talk and talk about some of the ways in which Adam might currently be broken and some of the ways in which we might be able to fix some of the problems that Adam currently experiences. There are a whole host of ICLR 2018 optimization papers that include On the Convergence of Adam and Beyond, Normalized Direction Preserving Adam, Fixing Weight Decay Regularization in Adam, Dissecting Adam, the Sign, Magnitude, and Variance of Stochastic Gradients, and Yellowfin and the Art of Momentum Tuning. So it's obvious that the research community has their eyes on Adam as they try and disentangle some of the effects they're experiencing from using the Adam optimizer in practice. So what can we improve about Adam in practice? Perhaps the most significant shortcoming of Adam is highlighted in the paper, improving generalization performance by switching from Adam to SGD, which says, despite superior training outcomes, adaptive optimization methods such as Adam, Adagrad, or RMSProp have been found to generalize poorly compared to stochastic gradient descent. These methods tend to perform well in the initial portion of training, but are outperformed by stochastic gradient descent at later stages of training. And you can see a plot here on the right from the marginal value of adaptive gradient methods in machine learning, which shows this to be true. So we know that Adam generalizes more poorly than stochastic gradient descent, but I guess the question is why? One hypothesis is that the problem may be with the computation of an exponential moving average. Some features are rarely active, or some features rarely receive gradients in the machine learning model. When they are active, they provide large gradients. In this setting, exponential moving averages don't entirely deal with this kind of behavior because the influence of past gradients diminishes too quickly. So by the time your next gradient update is received, your estimate of how much you should update your model parameters is inaccurate because your factor by which you scale down the gradient update is inaccurate. Exponential moving averages produces this inaccurate estimate of gradient magnitude when gradient updates are sparse. So how do we fix it? Well, one potential solution is instead of storing the exponential moving average of past squared gradients, we can store the maximum past squared gradient and use that to adjust the size of the weight update. The resultant algorithm is termed AMSgrad by the paper on the convergence of Adam and Beyond. And AMSgrad enjoys some theoretical guarantees that are missing from Adam. Researchers then show that this empirically leads to better generalization performance. Here you can see the update rules of AMSgrad on the right. It's just a slight modification of Adam. And this is actually something that should be available fairly soon as an argument that you can pass into the Adam optimizer in TensorFlow. Another potential problem with Adam is that the implementation of Adam is in conflict with the typical implementation of L2 regularization. So using L2 regularization in combination with Adam does not allow you to take advantage of the benefits that L2 regularization typically provides. In particular, L2 regularization is typically implemented as an addition to the loss term of the model. When combined with adaptive gradient methods, L2 regularization leads to weights with large gradients being regularized less than they would when using weight decay. Weight decay is the original formulation of an L2 penalty, where instead of adding a component to the loss term, weight decay simply subtracts a fraction of the weight at each gradient update. Using L2 regularization in conjunction with Adam is not effective, but using weight decay in conjunction with Adam is. So they propose a modification to the Adam algorithm that does exactly this. And they show that the resulting model is less sensitive to hyperparameters and finds flatter minima. Yet another hypothesis for why Adam experiences problems with generalization is that Adam and other adaptive gradient methods set a learning rate on a per parameter basis, and this leads to adapted gradients which differ from true gradients. So in other words, the updates of your model are not in the same direction as the updates of stochastic gradient descent. Here we're trading reduction in the variance of update direction for an increase in the bias of the update direction from the true gradient direction. This was highlighted in the paper Dissecting Adam, the Sign, Magnitude, and Variance of Stochastic Gradients. And you can see an illustration of that point above. So how do we fix this problem with gradient direction bias? Well, the paper Yellowfin and the Art of Momentum Tuning suggests that adaptive learning rate methods might be the problem. So instead of using individual learning rate per parameter, which leads to a different update direction than vanilla stochastic gradient descent, what if we only used a global learning rate? And we solve the learning rate setting problem separately. So in other words, adaptive learning rate methods were created because we had trouble setting learning rate hyperparameters. If we instead found a better way to set a global learning rate, we might achieve similar results. And that's exactly what Yellowfin saw in practice. They implemented a learning rate and momentum rate tuner with a negative feedback loop that monitored gradient values. And they found a method which requires no hyperparameter tuning, and in their tests led to faster convergence than Adam. Here's a plot on the right where you can see a comparison of Yellowfin and Adam. So in general, Adam generally performs well, but it does have its limits. In particular, at the upper limits of training data volume, you should experiment with SGD plus Nesterov Momentum and learning rate annealing, or a method like Yellowfin to see if you get better empirical results. Consider using weight decay rather than L2 regularization in conjunction with Adam. And run a comparison against the recent paper which proposes Adagrad as a solution. Most importantly, monitor archive.org, wait for academia to figure out and disentangle the causes of the lack of generalization behavior in Adam before deciding whether or not it's time to move past using Adam as your default optimizer. For the most part, Adam's still a great go-to that enables you to tell whether or not an approach or a new model architecture is going to work with very little effort. And I don't think it's time to move past it yet. I wanted to finish with a couple quick shoutouts to some other great content. First of all, definitely check out Sebastian Reuter's blog, available at http://reuter.io. He has some of the best content on helping engineers understand optimizers and understand gradient descent, and his content forms the basis for a large part of this talk, so it's definitely worth a look. You can also check out Chapter 8 of the Deep Learning book by Ian Goodfellow, Yashua Bengio, and Aaron Coraville. This is an additional useful supplement to this talk. And finally, check out Feifei Li's CS231N course, which has a great list of practical recommendations for training neural networks and talks a bit about how optimizers can impact model performance.